Share. I hope everyone also remotely still sees the screen. Otherwise, just tell us. So the last thing that we ended with, and before we go on to giving you some tools that you can use for this like data exploration in the different groups, is that we were discussing how to actually optimize the resolving step, right? And I just told you that with like double shift or control F. Okay, need to hide this again. Or control F, you can open this little quick search and type in local minimum feature resolver and just enter to open it. If you cannot find it, there's on feature detection and then chromatogram resolving, local minimum resolver, and you can see there's many other ones. And there's like some papers that show that the ADAP resolver, for example, is better for GCMS data and so on. It's personally, I think it's harder to optimize, and it's like has many more parameters that like are hard to grasp. So we typically say start with the local minimum resolver. It's also the one that is very much optimized for speed. So if I click on show preview down here, and you can follow along if you still have it open, and then click on feature list. So local minimum feature resolver, show preview, and then feature list, we select something that has SM at the end, smooth. So extracted ion chromatogram smooth. We can already select different samples, and we can see that it's very much tries to, yeah. Did everyone open it? If you have some issues, yeah, Stefan is going around, Corinna is going around. So those thumbs. Yeah. So very much like you open the preview, you select one of the feature lists, and you can select different ones. You see that there's different masses being picked out. And it's very much just to give you some idea of like kind of like the worst case, which is up here, which is just a, just something that might be in the water, and then we ramp up ACN, it goes away, or it might be something in the ACN, might be in the air, right? So there's just some contaminants that are always there. And now on the bottom, it tries to find some features that actually we want to kind of separate and still retain. So it tries to give you some good-looking features. Let me see which one I actually am gonna. I guess I'm gonna go for one of the blood samples. So yeah, and in here, we're gonna perform some optimization steps. So in the beginning, it might be that all those settings are suboptimal, let's say. And I'm gonna worsen it. Oh yeah, worsen it a lot. So let's say, oh yeah, well, that's already kind of bad. So you saw there's like number of little things here exploding. That was like all the features that is detecting from one chromatogram. And you can expect there to be thousands of chromatograms. And we want to split them into thousands of features, but very much depends on the complexity of your data set. And if we have something like here on the top, I would rather discard the whole thing and not find any features than having 100 bad features that are just going to clog up my analysis, because also the processing is going to take way longer. So to optimize this, there's a bunch of parameters, and we've seen that minimum ratio peak to top to edge was already improving it a little bit. And this is very much like how much of a difference should there be between the edges and the top. And of course, if we have something like a double peak, we're going to have like an edge that is shifted a bit more to the top, and then try to find one of those. But especially for those noisy features on the top here, it's going to be very important to just cut them out. And the best way to cut them out is actually there's like chromatographic threshold. And this is also one of the parameters that again looks at like how many real data points can we expect for an LCMS feature or LCMS extracted ion chromatogram. Yeah, like how many different peaks can there be separated in this range? We have 9 minutes now here. And within this 9 minutes, only like a very small portion of this might be actual data. So with 85%, we actually sort all the data points by intensity. We cut away the 85% like least intense. So it's a percentile intensity filter. There's kind of like 50% is going to be the median of the intensity in the chromatogram. Yeah. And so with this, it's usually good because it already cuts away so many of those features. Now, even if I say with 1 minimum top to edge, this is like no filter basically. It still doesn't detect so many features like before. Yeah, so this filter actually does something. And really, if we say one feature had like 5 to 6 data points, there is not so many data points that we expect to be real chemical data. Then this one was at 0.045. Minimum relative height, I would not set personally because I rather want some absolute height. So the relative height in a chromatogram would be there's a very high signal, and then there's a second peak. And when we set it to like 1% minimum relative height, it would just cut out some very proper normal features that like otherwise would be detected. And so I rather set something absolute here and just leave this to 0. We had this one to 1E5. So of course we can also set it there. And we had the minimum ratio top to edge was somewhere around 2. Of course, we could go back to the batch mode. Yeah, so I can go into the batch mode here. So just on the menu here, project, batch mode, and we have the same step here, local minimum feature resolver. We double click, and in there you can see it's very much what I said. It's like 85, and here's 2. And the same thing is what I'm setting here right now. Yeah, so if you set the same parameters, it should be like kind of the same here. So 2 top to edge. And now, how do we usually optimize this? So again, like on the top, we already have some noisy feature. And on the bottom, it's usually good to just go through your feature list maybe and even find a peak that has this like double peak. Yeah, so like not a perfectly separated feature, but we can also sort, for example, by area, maybe. Takes a bit of time, and it's actually hidden. No, here. And then we take the second drop down, and now we have to go all the way to the bottom because it's sorted in this way. And we see there's a lot of trash actually coming down. Let me see. Just have to try out some, so we can also click on this. If the screen is larger, it's also a bit easier because then we can just drop it down and we can just go through with arrows. And here we have a like perfect example. It's very intense peak, right? So it's maybe not the most representative, but at least we got something that is not very much like baseline separated. So we want to find something like on the top and on the bottom. And then we can go and we can say, okay, 85 actually does not change anything for the bottom one because it only captures like a little bit of range here. Then most likely it's actually the minimum search range, which is too high when you have 2 peaks being merged. So we can just try to lower this. And if we lower it here, for example, to 0.03, we already get 2 shapes. And we can see if we lower it even further, is rather going to be kind of truncated sometimes. Yeah, so sometimes it's then finding like minima too early. And of course, this is something like we want to improve on in the future, but the take-home message is mostly that there's usually not really like perfect parameters for all the features. Yeah, so you always have some trade-offs. But usually like going in here, finding those like very closely eluding peaks is good to set parameters that work for this. And then of course we would go in the drop down and maybe go through some of the other features. And you can see like this one is very hard to even make out as an expert to say what's happening here, right? Might be that it was like mixture of the injection was like too much ACN or something, like methanol or something in there, or might be overloaded, might be 3 compounds, might be 2. It's very hard to tell, right? But at least it's good to just look at a few different examples and then see what happens to them if we change those parameters. And so typically it is really like we change this one and we usually keep it at like 80–85% because more data we don't expect. Then there's the minimum search range, which is very dependent on the length of your chromatography and the resolution of your chromatography. So for like a 9-minute gradient UHPLC, you typically have something very similar. And then we have the absolute intensity. So minimum absolute height is also something that just needs to be sensible for your instrument, for your settings. And if you're working with thousands of samples, I'd rather increase this and just hope that in enough samples, it was triggering like it was higher than that. And then later in gap filling, we would fill in the missing features that we missed in the first feature detection, because otherwise it's just going to explode. And also like the minimum top to edge is very much one that you have to optimize. Again, if there's something like this and we increase it too much, because if we raise it, we are stricter with the requirements, and then the left border of the second peak is not high, is not like low enough for the intensity of the feature. Yeah. And so if we now have this and we just want to apply it to all the matching feature lists, it's kind of annoying. We typically have to like select all the ones that are smooth. But for this, we actually have multiple different ways to select in this like manual way, multiple different ways how to select it. So as selected in main Windows 1 here, feature lists. And if we change to feature list name pattern, we can go and select. And then in here, we can type in *SM. Yeah, *SM, because it's going to end with an SM and we allow everything up front. And it's actually selecting 8 files. Yeah, so if I just run this again, you see that for each file, we're now producing a new one. And in this case, actually, I set the suffix to resolved. So we can even distinguish between R and resolved. Yeah. Okay, so this was a lot, I guess. But for now, I just want to show you one more thing, how you can look into data. Then we're going to process the 88 files, and then you can have some time to talk to your group members, to talk to your neighbors, and just explore the data set so that you also have some more insights once we go to all the other tools and maybe get some more annotations from series and so on. So, yeah. Yeah. So yeah, like the selection is quite important, and it's like in all those modules. So if I open any of those modules, most of the time they have raw data files or feature lists on the top as a parameter. I can here drop down and then say feature list name pattern, and then click on select. And then I can put something like *SM. Yeah. So in this way, you could even you can also use that in a batch mode. And in the batch mode, it would actually then, you could set up like different thresholds, and you could even splice it open into like 2 different processing steps, like low filtering and high filtering, let's say, right? And you could process it twice. And then you just do * as a wildcard, so you allow everything, and then SM. And maybe also here, like in batch mode, there's usually sometimes when you rerun things and you only want to run a few steps, there's sometimes this, like your feature list is always set in the batch mode usually to those created by previous step. Yeah, so it usually wants you to kind of run it in a sequence and then just pipes in the results from one step into the next step. And so then you also have to change this here, or you just rerun it from the start. Okay, so one thing that we wanted to show you now for the exploration part, we open the feature table and you can follow along. Open the feature table, and then in here, I'm going to look for annotated features again, because we want to first start from here. I can right click here. So I did scroll over to spectral matches. If they're missing, just toggle the library matches here. And then I right click and go on show feature overview network. Yeah, so right click on one of those rows. It's definitely going to be interesting if it has an annotation, but you can also do it on any feature actually. And then show feature overview network. And it's going to open a new dialog. And in this dialog, you see those networks that we just discussed earlier. And okay, it doesn't work if I yeah, so we double click on any of the feature lists to open it, right? So the aligned feature list, so the topmost feature list and aligned, so here. So aligned feature list, and then the topmost feature list, we double click, open this. I did sort by spectral matches because then I at least know that something is known. Yeah, so I sorted twice, so click once and twice. And then if I right click, show, and feature overview network. And from here, so yeah, maybe also if some people have problems, I mean, there's going to be a lot of time of trying that out, and you can talk to your neighbors, and also Corinna and Stefan going to walk around, and if individuals have problems, yeah, you're going to be able to open it at one point. So it's really just like on any of the rows, right click, show, and feature overview network. It is, I have to say, it is only in version 3.8 and 3.9. Yeah, so the last two versions. So that's 13 hours of train ride. So, and you're the second ones to try it out. So it's kind of tested, you know? Who was not able to open this? Okay, everyone else is kind of confused. Did you, oh yeah, sometimes. So sometimes definitely like the feature list, sometimes when you sort it and do some things, sometimes it's good to just close the feature list. So you just X on the feature list and you just reopen it. Yeah, you just double click on the aligned feature list again, you reopen it. Sometimes it does things, you know. But yeah, and maybe also for Mac, I mean, maybe like control click for right click, but I don't know.
Closing it. So,
okay, closing and opening actually saved the day for some people at least. And I only want to highlight like some features that you can use here and that you can also use to understand, first of all, like molecular networking as the concept for tomorrow, but then also kind of explore the data set already. So in this view, and it's kind of big for me, so I don't see it very much. So in this view, we got the spectral library matches on the right side, and we did select the vanillin here. And on the left side, we have a network. And in this network, we have those like blue edges. Yeah, see there's like actually like dark edges and light blue edges, and then some red edges, orange. But so the idea is that we focused on vanillin, and we wanted to get all the chemical neighborhood of vanillin. Yeah, so we clicked on it, we opened this dialog, and then it shows us the first neighbors based on spectral similarity. So I can drag it out, and you see there's some dark edges, it's the first neighbors, and then there's some light blue edges, and it's the second neighbors. Yeah, so it's kind of this like two-step like modification, single modification. And now if I want to see, first of all, annotations, it's very easy. I can just click on the different nodes, and there's some annotated nodes here. So I just click on them and directly get the library match on the right side with the cosine similarity, with explained library intensity, which is just like how much of the signals in the bottom, so of the reference spectrum, were actually matched to something in my spectrum. And if I now just want to compare something, so let's say there was vanillin, and there's this little node down here, I'm gonna click on vanillin, hold shift, and click on the other node, and switch over to the similarity tab. Yeah, so you can all like switch over to the similarity tab, and you can select any two nodes. It doesn't have to be the same. So you just select vanillin or something, and then with shift, you click on the second node, and you can see that now we have two spectra on the top and bottom. And we see that some signals are matched in orange. That means the neutral loss was the same. Yeah, so the difference of the precursor precursor MZs is taken into account. But also if we zoom in, we can see that some of the signals are also like directly matched. Yeah, so like 93 point something was like a direct match, and there was another signal in one of the spectra that had no match. Yeah, but the orange ones, you know, they kind of look shifted, and it's hard to make out if they're really matching something. But you can switch over, like in similarity tab, you can switch over to the neutral loss tab, and then you suddenly see like, okay, neutral loss of the precursor signals is of course 0, right? So the precursors are basically flipped as the 0 is the reference point. Spectra are being flipped on them, and then we have the neutral losses of 27.9 and 42, and we can see that those are now directly matched. Yeah, so the neutral losses are the same, and it's here those like orange signals that are just being flipped. Yeah, if we switch between those two. And so you can go through these tabs and look at the similarity between different features. We can also look at similarity between different annotated compounds and so on. And we can also look at the annotations themselves. And we can also look at all the MS2 spectra. Yeah, so if I click on all MS2, and I, for example, select vanillin, I see vanillin. If I then hold shift and I just select more nodes, so I just really just select multiple nodes here, we can really see that there's a lot of different spectra being added, and all of those are MS2 spectra here. On the top is like a pseudo MS1 spectrum, so we just get like all the, I think we get like all the MS1 signals. Okay, I don't know the top, I actually don't want that here. But all the ones with an orange signal is an MS2, and the orange is actually the precursor signal. Yeah. And in this view, we can kind of see if there's like some signals being produced in the same like MZ range, basically. Yeah. So we can go through and look at multiple spectra at the same time. And just one thing, because we, let's see if I can find it actually. Okay, we can talk about it. I found it. There's diphenhydramine, and this was kind of like the focus of the study. And there's like if I just type in filters on the network view on the left, I can open the filters. I can type in diphen and it auto completes with all the matches that we got, all the annotations, yeah, and also the scores. And this is actually all for the same node. If I look here, there's like focus on one node, and I can click it, and then it focuses on this one node, and we can see that there's actually no neighborhood. So there's nothing similar enough, let's say, nothing that really had enough signals being aligned and also like the spectral similarity to match. And it's sometimes interesting to look into, right? So first of all, we get the annotations here, and it looks like a perfect match, right? There's one very major signal, and I need to just zoom in here. So if I zoom in on the signal, that's like a perfect match, right? But then there's not much more. Like there's some signals here. And if I zoom in, we can also see that at least like the relative intensity between those signals are very similar. And also if I had enough screen space here with a zoomed in one, I would see that maybe even like the fragmentation energy that they use on this thermo Q executive is pretty much the same that we also used. Yeah, it's like it's actually a perfect match. So maybe it's actually the spectrum that was supplied even. But yeah, so basically, yeah, that's also one thing to ask, right? But so basically we see that for some compounds, for some compound classes, the spectrum might just be very simple, right? We got a neutral loss here, and if something changes on the structure that was split off, it's very likely not going to change the spectrum a lot. Yeah. And so once you set out to analyze all your samples, you can just use that and type in some compounds here, search them up. And then if you click on focus, sometimes you have to click twice. It's going to show you, pull out the whole network. And also you can, in the visuals, just change a few things and kind of look at different things. So if we go to visuals, there's like node labels, for example. Maybe we're interested in the retention time, so I can just change over to retention time. We also see that the color by default is also retention time. So everything that is very dark is very late in the chromatogram. Everything that is lighter is very early. And the intensity and so on is scaling the nodes. So yeah. So, and in this idea, like in this view, you can very much just go through and just like quickly visualize data. And one more thing, you can also click on a node. So we already did this like focus on one node. We could also just select, actually, yeah, we could select a few nodes here. So let's say we select 1 and 2 nodes and we click on focus. It's really pulling out the neighbors from both of these nodes. Yeah, so now we have a network where 2 nodes are the center and everything else is then like 1 connection and 2 connections away from that. And you can set up the number of connections here. And very much later also with GPS, we're going to see that like the networks are way more complex than this. So this is really just a zoomed in view into the networks. Yeah, so you really just have the neighborhood and you don't necessarily see the whole network like in Cytoscape and GPS, where you might be seeing something more like this. And this is without filtering applied. So the networks look very, very like messy somehow, right? But yeah, like this is, in my view, more like the relationship within your data set that many things are similar to many things. Okay, and again, there's like the cosine similarity threshold that we used was 0.7, so 0.7. And if you decrease that further, it's going to be clustering even more, but you could also increase it more, and we try to make it easy to apply. Okay, so with this, we're going to run the batch now on all files, and then we can just leave you up to processing. You can ask us some questions, and everyone can also just work in like with their neighbors and groups, and we're also going to be walking around. So please follow along. For this, we at best just close the project or close MZmine and just restart MZmine. Doesn't matter. We can close the project so that we just clear up everything in the feature list and MS data files. Also, maybe close all the tabs that you have. And then in the processing wizard again, we can now say that in subfolder. So we open the processing wizard, and first of course, you hopefully saved all the presets. And I did send like a slide deck on the shared slides. There's a slide deck with all the parameters that we set. So you can also go from there, or I can come around and yeah, can help you set it up again. So I load the preset. So I go on local presets and I have the summer school here. I load it. I now have to define all the files, and the easiest way is usually in subfolders. So I check mark the in subfolders, and then all MZML files. If I do this, and I select my summer school folder with all the files in there, it's going to pull out all the files. Make sure that you're not selecting like a folder where you have like all 3 data sets, like group 1, group 2 examples. Yeah, is also okay, but that would be a bit too much. Like you can just run on your groups folder. And then for UHPLC, we also set that proximate feature for width half maximum. We could optimize, and we did change it to 0.03. And also the RT tolerance was 0.4, right? So we're going to change it to 0.1, which is still kind of like giving us some space for like shifts in the retention time in like 88 samples. But then it's not too strict and not too open. Okay, so UHPLC 0.03 and this, and then Orbitrap should be all the same. We didn't change anything. So it's like MS2, we did put to 2, and then here's like 1E5. And filters is now the thing that we're going to change. So we optimize our batch. We're like kind of happy with it now, for now at least. I can tell you're going to do that many times and you rerun and rerun. But, you know, we're going to change this original feature list now to remove, because now we want to run it on a larger batch. And so we don't need to keep all the intermediate steps for backtracking of errors. So we do remove on filters, and annotation stays. So make sure the library's in there. And then on DDA, you can leave it to the same files, but just make sure that maybe, yeah, that like the file name is the same and so on, so that you overwrite those files. We're going to use the same files later for other steps, so it's not going to make such a difference here. And then we can save again the presets, and it should still have our old name. So I'm really just like clicking save presets and okay. I would always do that because then you keep the settings. Then we go on create batch. And now I just need to see everyone's there. So you got the 88 sample selected. Yeah. Yeah, I can show them really fast. UHPLC was 0.4 minutes to 9 minutes. And again, like we have some files prepared for you. So we're gonna like later work with other files. It's not gonna make a huge difference now what you really do. You cannot break it. And then there's minimum consecutive scans 5 and 0.03. This is what we changed. And sample to sample 0.1. And with the Orbitrap, we didn't really change much. It was 1E5 as the feature height. And then for MS2 MSN was 2, a factor of 2, because the spectra are already kind of clean. You can tell after they are imported. During import you can tell. Yeah, I can show you. Yeah. But yeah, good question. Sometimes I'm asking myself, how can I know how many files I have? So okay, so we're gonna help everyone to get that run, but I want everyone to just get a quick start and just run it, and then everyone who has some problems, we can go around and fix your issues. So very much, we set it to remove and we saved it. And now we click on create batch. This window again is the most important one. And we then also click on save here. Yeah, save. Because this file is so crucial. Yeah, so I'm gonna save it as the summer school XML. And personally, I just have like one batch folder, so I don't put those batches to my data set. I just have one because they're not so different, so I can reuse them very often. And then otherwise, I have so many versions flying around, so I just have one batch file folder. So you save, give it a name, and save. And then this file configures the whole processing step. So you save that, you share it with your publication, you share it with the reviewers, and so on. and it's going to be very easy to reproduce. And then you just click OK. And hopefully when I now click on task, like on the taskbar on the bottom, so maybe you close the task here on the top. Oh, it's actually, yeah, I zoomed out, right? So yeah, so if you, my screen is the wrong size for the projector, so it's, yeah, like down here, if you just click on those, there's like taskbar on the bottom, it should open the task here. And yeah, and then here you should see there's like 88 tasks, or like 98 actually, right? If you click start, and then it should do like 89, I think, right? Yeah, that's what I wanted to say. Yeah, 89 tasks. And you can also see it's like importing all the files. The spectral library was already imported, so if you didn't close MZmine in between, it should just do all the processing. It's a lot of data to parse and to import, but we handle it in a way that we, yeah, like offload stuff to temporary files. And as long as you have enough like fast SSD storage or something, it goes very fast. You should not care about it. And so you see, it already takes a bit longer, right? Like before, it was maybe, at least on my laptop, was like a minute maybe to run like on 8 files. Now we're already detecting chromatograms. We can see here that now it's detecting chromatograms, and once it's going to smoothing, it's actually going to erase all the other feature lists, and it's going to produce new ones. Yeah, so smoothing is done. So you see like all the other ones are always deleted. And some questions that always come up is like, MZmine eats so much memory. So maybe some of you ran into some memory issues in the past with MZmine. So there's like 2 things to it. Like, of course, especially in the alignment of samples, that's a very like memory hungry step, especially because there's a lot of features and a lot of samples that you want to align your features in. And so there it's very much important that if your study scales, of course you can try your old parameters, but maybe it's also better to just raise some of the thresholds and raise some of the filters, and then just rely again on like the gap filling, because alignment and gap filling are fully parallelized, so it runs all in parallel, and it's going to be quite performant there. And the other thing is Java applications. You can see on the bottom there, there's like a memory overview, like how much memory are we using and how much memory is free. And Java's kind of lazy. It's just going to grab all the memory that's there if it needs to, right? And it's not directly like freeing it for other tasks. But if there are other tasks and Java does not really need the memory, it's also going to let go at some point. But it's very hard to profile those things. Like just looking into the task manager with the Java app and just saying, and I think the same might be true even for Python, but like just looking into the task manager is not going to show you like the real memory that is consumed, because Java manages that. Yeah. So there's always like a garbage collector basically running and like taking all those old chromatograms and old feature lists and whatever that we discard off, always taking that and bringing out the trash very lazily. Yeah, so only if we really need to, it's going to bring out the trash. And yeah, so that's it. It's running. It's going to produce a very similar output. So there's going to be one feature list. And this one feature list, you can then open, you can explore, you can open the different raw data files, look into the raw data file overview, and also kind of like try to find the different annotated features and all those kind of things, and kind of discuss maybe also with your neighbors, like what kind of problems they usually have and what kind of problems they usually face in like data processing, and also like running the machines and optimizing methods. Okay, so we're mostly done. We're exporting a bunch of things here. And maybe just one more thing, because many people also want to use some of the figures for publications. They want to create reports and so on, right? In MZmine, we try that like all the charts that we produce can be exported. So if I zoom into any chart here, this is actually two charts. If I zoom in and I right click somewhere in the chart, I can say export graphics. And with export graphics, I can define it, for example, as a PDF so that I really have the text objects and the lines and everything. And I can later drop it into Illustrator. And then I can really like manipulate everything in a good way, right? Like I can change colors. I typically even have like everything in one Illustrator file, and then I can recolor everything at once. I can say, this orange I don't like, I want this other orange. This blue is not the same blue as the other one, so I'm going to change everything at once in one thing. And so PDF is definitely very good. And then, of course, for very like, I don't know, like charts that are full of objects, sometimes it's also nice to just say, okay, PNG, and then there's a pixel graphic. You can easily skim through and look at that. You can set the width and height, and you can already make it like a like one column or double column figure. Yeah, so you can already do all this, and then you just say apply, and also apply the theme and renew preview, and then you just save it, and you can do that with like individual charts. But also in MZmine, and there was one option in the wizard even, you can now also export, wait, oh yeah, export annotations to PDF. So annotation, graphics, export. And in here, you already see there's like a bunch of options. And if I really want to, I can just export all the shapes of the peaks, the MS library matches, the lipid matches, and all of those kind of things. And I can export it for a feature list. Yeah, so like all the features are going to be exported. And then later you can just skim through. And so you don't have to open MZmine every time to just look at the library match, for example. Yeah, it's just something that you can try out on your own and something that you can use. So double shift and then export annotation, and then it usually shows up here. Or feature list methods, export feature list. I think those are like the most important ones actually in MZmine, because at one point, everything that you can do in MZmine is kind of like exhausted. And then you also want to use all the other tools that are being developed that make great progress on annotation, on processing, on spectral quality, on everything, right? So, and those modules here for exporting, they very much help you there, right? And if something's missing, report it and, you know, define the format that is needed. And then hopefully in the future, we can implement that. Okay. And so yeah, we produced output files, and you should see that in this folder that you selected, you now have a bunch of different files, and I cannot really zoom in, I don't know how. But yeah, so you're going to see that there's a bunch of different files, and we're not going into detail here now, but you can already see that there's a Sirius file, like Sirius MGF, with all the spectral data that we send to Sirius. There's some GMPS files that we send to GMPS. And then there's also, for example, the annotations file where we just have all the annotations. And we also got some GraphML files. And those GraphML files, we can also drop into Cytoscape and do networks there. Okay. Yeah, that was very long session, I guess. But we hope that you got some insights into how to look into raw data, how to optimize feature finding, how to maybe also navigate the results in MZmine, and you got some time to go on. And it's like 1 hour still. There's going to be a coffee break. Very nice. I forgot about coffee breaks. And there's also going to be another tour, right, of group 5? Group 4. Yes. Okay. That we will work with tomorrow. They are uploaded for every group on the GitHub repository. We'll send out email later on as well, so everybody download
And yeah, so we are all on the same page, and the other workshops can continue as planned.
Yeah, so very much what Stefan said, also for the online participants that might have not heard it. So on the GitHub page, there's already some section on MZmine, and it's very important, there's even bold here, important notice, that we do need to download the output files if you really use the same files and really use the same parameters that we did, but we don't even know, that you should have reproduced the same output files. But again, it's just easier to download those files. And you can just go here and download all those files, and then you can use them for the next sessions for the next days. Yeah, so that everyone's on the same page. And yeah, so I guess there's a break.
Yeah, say that.